So, hello everyone. This video will be replacing the session that we were supposed to have on the 23rd. I have an emergency to not to be able to teach, but the lesson will be recorded and then you will be able to submit your questions if you have any. And then we will have another session in which we're going to continue the module 4 and also answer all the questions you may have about the lesson 4.1, 4.2, and 4.3. And then in the same session, we may go over some of the questions about the test number 4 for module number 4. So hopefully the video is going to be helpful, and then you may feel free to submit all your questions between now and next class before test number 4. So let's get the lesson started. So in this lesson, we'll be covering content for homework 1, module 4, homework 2, module 4, and homework 3, module 4. Homework 1 will include these elements: exponential functions, the features and how to graph the exponential functions, compound and continuous interest, and other application. So let's get started with what's the basic form of an exponential function. So the basic form of an exponential function is going to be b exponent x, where b is a positive number greater than 1. I'll say a positive number not equal 1. Not equal to 1. So, and then we will have the general form of an exponential function. The general form of an exponential function, when you include all the transformation, I'm talking about h and k, if you remember from the previous lessons. So the general form of an exponential function is going to be a b x minus h plus k. A, and if you remember, a will be responsible of vertical stretches, or also the vertical strengths. So A would be the factor. The factor A would be vertical stretch or vertical strengths. So H is going to be all the horizontal shift. And K will be what we call the vertical shift. And then also, now let's talk about the domain of exponential function. The domain of an exponential function is always going to be all real numbers, negative infinity to positive infinity. And the range of an exponential function is going to be, it's going to be negative infinity, k to positive infinity if a positive, or negative infinity to k if a is negative. Now, how do we find the y-intercept? The y-intercept of an exponential function is always going to be when x equals 0. So y-intercept, that means the value of y, an ordered pair that you need to obtain when x equals 0. So now when x equals 0, you're going to have a point with 0 as the x coordinate. And then the y coordinate, when you plug in 0 in this equation here, it's going to give you whatever you need for y. And then y is going to be, this part's going to be 1 when you plug in x equals 0. So 1 times a, it's a, and then plus k. So basically, the y coordinate for the y-intercept is going to be a plus k. What k and a are, you just have to add them to find the y coordinate of the y-intercept. And now, what is the horizontal asymptote? Horizontal asymptote is always going to be this line. If you have the line like this horizontal line, x, y equals 0 is always going to be your horizontal asymptote. So that the x-axis is always going to be your horizontal asymptote in the basic function, of course, in the basic function. But when you translate, the horizontal asymptote is not going to be y equals 0. It's always going to be whatever k represent. So y equals k. If k equals 0, then you would not have the k. The horizontal asymptote is going to be 0, but if k is there, it's always going to be y equals k. And the vertical asymptote, of course, is not going to exist. That's why I put NA. And the graph of your functions is going to be either this one to say that this is a growth exponential function, or decay, where the exponential function is decreasing exponentially. So basically, to have this graph is going to give you when b is greater than 1. And your graph decay is going to be when b is less than 1, is greater than 0 always, but less than 1. So whenever you have b in between 0 and 1, your graph, your exponential is an decay when b is between 0 and 1, already positive, but less than 1. But whenever b is greater than 1, you have an exponential growth, and your graph is going to be increasing. So one of the applications of exponential functions is calculating interest. So we're gonna see now the compound interest and the continuous interest. The compound interest is this formula where A is the final value of an investment, P is being the initial investment, N is the number of time this investment is being done per year in a year. R is the interest rate of the investment, and T is the number of years that the investment is being processed. So that's the same thing over here. The only difference is that in a year, for the only difference is that for the continuous interest, there would be no number of times in a year that the interest is being processed. It's going to be continuous, which means there will be no N. That represents the number of times the transaction is being made in a single year. So let's go ahead and do one example that includes different values of the parameters so you can understand the process. Here is an example. It says find the accumulated value of an investment of $10,000 for 3 years. $10,000 is being the P value, the value of the invested value. 3 years is being the T. That means the number of years the investment lasts. 5 at the interest rate of 6.5. 6.5 divided by 100, that's going to be 0.065, which is the interest rate. R equals 0.065. You always have to divide the percent by 100 to find the value in decimal of the interest rate. Now, 4 questions. A, they say if the investment is being compounded semi-annually, which means you're going to have a N value that equals 2 because you have 2 halves of a year. Secondly, B, quarterly. Quarterly, that means you have 4 quarters in a year, so that's N equals 4. Monthly, how many months you have in a single year, that is N equals 12. And continuously, there will be no N because it's being compounded continuously. When the interest is being compounded continuously, that means never stops in a single year. So you will not have an N value that will determine the number of times the interest is compounded in a single year. So question A, semi-annually. So A, which is the value of the end value of the investment, A, equals P, in this case P, 10,000, times 1 plus the interest rate 0.065 over N. N in the first case, N equals 2. So A equals, you're going to have and you have to enter the values in the calculator. And then you're going to have A equals, and then it says round the values to the nearest cent. So that's going to be 12,115.45, let's say 47 cents. That's the value of the invested $10,000 for 3 years, compounded semi-annually. B, it says now, find the accumulated value of the investment of $10,000 if this investment is being compounded quarterly. Quarterly, that means you have an end value that equals 4. So, well, I forgot to put the NT on top. N equals 2, and then T equals 3. So T is 3. So then when you plug in all the values, I put it in the calculator, but I forgot to put it in the formula. So B, the only difference that's going to be, we're going to see for B is that this is being compounded quarterly, which gives me N equals 4. So N equals 4. So A equals, type the values in the calculator. N equals 4. The exponent is going to be 12, and plug them into the calculator. The answer is 12,134. The cent is 0.8. $0.8. Now C, compounded monthly, N equals 12. So C, we're gonna have the same parameters, but in this case N equals 12. N equals 12. A equals, we plug them into the calculator. N equals 12, so that's going to be 36 as the exponent. And then N equals 12, so that's 12,146.72. And then that's the amount of dollars generated over the 3 years of a compound interest, monthly compounded. And then D, this time it's the interest is being the investment is being compounded continuously, which will be A equals 10,000 times e to the 0.65 times the value of the time t, or t, so that's t times 3. Plug them into the calculator, and then you're going to have this result of A equals 12,153.11. So that's the amount in dollars of the investment if there is a continuous compound if the investment is being compounded continuously. So basically, all the other problems are going to be the same as long as you can understand when they tell you how the investment is being compounded. If it's continuously, then there will be no n, which would be the number of times this transaction is being made in a single year. For continuous, it's always going to be happening, so there will be no number of time in a single year that determine the n for the continuous. Otherwise, if it says semi-annually, then it's 2 times because you have 2 halves in a year. Quarterly, 4 times in a year. Monthly, 12 times in a year. And then you make the sense of how many times this transaction repeats in a single year based on what they tell you about how it's compounded. Okay, so we're gonna use this number 14 as an example to show you how to graph any exponential function. So as you can see, the base b here is less than 1. So that means you have an exponential decay. An exponential decay, which means you're going to have a graph that is decreasing. And let's go ahead and read what they want us to find. So basically, they want us to find the graph of G and F. They also want you to find the equations of the asymptotes of these functions. But before I do that, I'm going to engage in finding the domain and range of each of them, because we do need to know how to find the domain and range. But it's not that difficult because we already know from the lesson how to find the domain and range of exponential function. It's just to apply the rules. So domain here is going to be always, since it's an exponential function, it's always going to be from negative infinity to positive infinity. So that's the domain. That's the same for G and F. So that's the domain for F, and the domain for G is going to be the same thing. As long as it's an exponential function, it's going to be, the domain is always going to be from negative infinity to positive infinity. Now, the range of these functions, the range of the function f is going to be from 0 to positive infinity, because there is no translations, or there is no translation up or down, left or right. So that means it's start right from 0. And that makes the 0 here, that makes it the equation of your horizontal asymptote. So that means x equals 0. X equals 0 is the equation of the horizontal asymptote of this function, of the function f. So horizontal asymptote is y equals 0, which is this line. Y equals 0 is going to be this line here. I like to put my horizontal asymptote in dotted lines. So increase the size and put it in dotted lines. So that's my horizontal asymptote. I want to put it in a different color as well. That's the horizontal asymptote for the function, the function f, because that's where it's going to start on the y-axis. And what would be the range for the function g? The range for the function g is going to be that number, whatever it is. That's how you start it, because that's the number that translates the graph up or down, and that's where you're gonna start. You're going to, that's the horizontal line that the graph is going to lean on. So if it's 4, the graph will not go lower than 4. In case that a, the coefficient that is in front of the function right here, is positive, so the graph is not going to go lower than this value. And then now you're gonna see the range is going to be from that value 4 to positive infinity. That makes the equation y equals 4 the equation of the horizontal asymptote for the function g. So we can also graph this one too. That's going to be 4 here. And then to increase the size, and then dotted line. So that's going to be the horizontal asymptote for the graph G. We have the domain, we have the range, and we also have the asymptotes. And we also know that this is a function, that a decay graph. So you are going to just show the graph in the coordinate system. So you know how the graph of a exponential function is presented from the note. Then we're just going to graph this function here, find the y-intercept where it touches the y, and then that's a graph for both functions. The function, that's a parent function. So this is going to, the pink is the basic function, and the blue is the transformed function. So basically, when I say basic and basic and transformed, so that's going to be g of x is going to be, f of x is going to be in pink, and g of x will be in blue. So that's it for this example. And then that's basically what you should do when graphing an exponential function. You should find the domain, the range. Maybe you don't have to, but if they ask you, that's how you're going to process. You're going to need to identify whether you have a decay or a growth exponential function. Find your horizontal asymptote, because the vertical asymptote does not exist for exponential function. And then you sketch the graph taking into account the shape of all exponential functions, and also you need to take into account the equation of your asymptote. So the horizontal asymptote for the first function is y equals 0. Is y equals 0 for f of x, and then equation for the asymptote for the function g of x is going to be y equals 4. That's this 4 right here for the function g. And then you're gonna see clearly that the graphs, they don't go lower than these asymptotes. They don't touch them. They get closer and closer to them, but never touches them.
So that's the example, and that's pretty much how you're going to process to graph your exponential function.